Hello, these are the solutions to AP Physics 1's homework number 4.1. So this is the first homework in Unit 4, which is regarding momentum and collisions and impulse. And the very first question is a straightforward one, just to calculate the magnitude of the momentum of a 28-gram sparrow. So, while it is perfectly okay, technically, to use a mass that is in grams, most of the time in this unit, we are going to want to convert this to kilograms. So I'm going to go ahead and do that, dividing by 1,000. 28 grams is identical to 0.028 kilograms. Then the velocity, or really the speed, since we're not sure about the direction, is 8.4 meters per second. And here we just use our simple formula for momentum. Momentum is equal to the product of mass and velocity. So momentum in this case will be 0.028 multiplied by 8.4. And if you follow the units, we would end up with kilograms times meters per second and get an answer for our momentum of 0.235, I'm going to round it, and units of kilograms times meters per second. So these are awkward units, but you do need to know them and you do need to write them. For question number 2, we have a constant friction force of 25 newtons acting on a 65 kilogram skier for 15 seconds on level snow, and we want to find his change in velocity. So let's go ahead and write these down. We have a force, and you can label it a force of friction if you like. I'm just writing the one force though, of 25 newtons, and it's acting on a skier with a mass of 65 kilograms, and it's acting for a time of 15 seconds. So I can write this as t. You may also think of it as delta t since it is a time interval. Both are acceptable. You can write it with or without the delta. And I want to know the change in velocity for the skier. So with these 4 things in mind, we want to use our newer version of Newton's second law. So remember, our new version of Newton's second law says that force, or the net force, is equal to mass times the change in velocity of an object over some time interval. So we're looking for delta V in this case, so we're going to isolate delta V in this equation. So when we do that, we are solving, and we see that we would have F times delta T divided by mass is equal to delta V. So let's substitute. Our force of 25 newtons, and actually, now that we think about it, this is very likely meant to be a negative, but we'll address that when we get our number, over a time period of 15 seconds for a mass of 65 kilograms. So when we calculate our delta V, we see that our delta V is approximately 5.77 meters per second. And since this is a friction force, we know that it's actually going to be slowing down. So what we may do is we may want to say that our friction force is a negative force. If this is negative, that makes our answer negative as well. And so we would kind of expect this because friction will tend to slow down our object, so our change in velocity should be negative. For number 3, we have a railroad car that travels on a level, frictionless track with a constant speed of 15 meters per second, and a 3,350 kilogram load is initially at rest and is dropped onto the car. So here's my car, it's moving with some initial speed, and we'll say that this is V1 for the car, and that's 15 meters per second. And it has a mass of 7,150 kilograms. And then above this car, we'll do a slightly different color. Let's see what goes with orange. Green. So we have a load up here, and it has an initial speed. So this is V1 for the load is 0. And it has a mass of 3,350 kilograms. So this is initial, and then these things kind of coincide. So we'll have the same cart still moving, but on top of this cart, we're going to have our load. So we know that after they kind of combine, they have some common velocity, and we'll just call that V2. Since they're both going to be stuck together, we're going to have some V2 where they're both moving together. They have to have the same velocity afterward. So let's set up our conservation of momentum in order to figure out what this new velocity is. So momentum 1 is equal to momentum final. And for each mass, that looks like, so this is mass of the car, I'm sorry, should use subscripts. Mass of the car and mass of the load. So I have mass of the car times v1 for the car plus mass of the load times its initial velocity is equal to, all right, so they're both moving together. So we can think about this as mass of the car times v2 plus mass of the load times v2. Or we can go ahead and just say it's one big mass that's moving together. So let's treat it as the sum of those two masses, both moving at v2. Now I can go in and I can say, all right, this is 0 because my v1 for the load is 0. And so all I have is mc times its initial velocity. So what am I solving for? I'm solving for this new speed v2. So isolating v2, just to do this symbolically, we have mc times v1c over mc plus ml. So substituting values, we have 7,150 multiplied by the initial speed of 15 all over the 7,150 plus 3,350. So plugging this into a calculator, we get a final speed of approximately 10.2 meters per second. And there you have it, conservation of momentum. For question number 4, we have a football question, American football if you're curious, where we have a 110 kilogram tackler. So we'll just say mass of the tackler is 110 kilograms, moving at a speed of 2.5 meters per second. So V1 of the tackler is 2.5 meters per second. And he runs head on, so we have to be careful about this, with a halfback moving at 5 meters per second. So if they collide head on, that means they are moving toward each other. So V1 for the halfback is negative because they are moving toward each other. They are moving in opposite directions, so one of them must be negative. Then the mass of the halfback is 82 kilograms. So afterward, they're going to stick together. We'll just say they're one big lump, and they're going to move. Now, we don't really know which way they're moving, so I'm not really going to draw a velocity. But if you would like to, you can think, okay, well, we'll just assume that it's to the right, but we don't know what that is. So let's figure that out. And to do that, we want to use conservation of momentum. So again, P1 is equal to P2, but let's do it one body at a time. So mass of our tackler times V1 of our tackler plus mass of our halfback times V1 of our halfback is going to be equal to, well, these two will move together, so let's treat them as one big mass. So mass of the tackler plus mass of the halfback times their common velocity, v2. Now I can't get rid of anything in this case because no velocities are 0 to begin with. So I just need to go ahead and solve for v2. So I have mass of the tackler times v1 tackler plus mass of the halfback times his initial velocity, or hers, all over the total mass. So now we can go ahead and substitute. So the mass of the tackler is 110 kilograms. The velocity is 2.5 plus the mass of our halfback, which is 82, times his initial velocity, which is -5 because it's going in the opposite direction, all over the total mass of 110 plus 82. So when we plug all this into our calculator, we find a final velocity of -0.70 is what we'll round it to. And that's meters per second. So even though we drew it where our velocity was going to the right, our result actually says that together they would move to the left after this collision. For question number 5, we're talking about a rocket, where the propelling gases are being expelled at a rate of 1,300 kilograms per second. So this is similar to the example we did in class, where we are given not just mass, but mass over some times. We're giving a rate for our mass, and that is 1,300 kilograms per second. Then these gases are expelled at a rate of 4.5 meters per second. So let's think about this for a half second. we have a velocity given to be 4.5 times 10 to the fourth meters per second. But for a rocket, these things essentially start off with no velocity. So really what we're given is a change in velocity. And one of the things that I know is that I'm looking for force. So putting all this together, I'm going to again use my new version of Newton's second law, where the force is equal to the mass times delta V over delta T, which we can group differently and say is the same as mass over delta T times delta V. So if I want to find that force, I've already solved for the force, so I can simply substitute. So my m over delta T here is 1,300 kilograms per second times our change in velocity, which is 4.5 times 10 to the fourth meters per second. And so you can kind of see where a Newton comes from in here, because you have kilograms times meters over seconds squared. So plugging this into our calculator, we get a force of, it's a large number, so I'm going to use a scientific notation. So it's 5.85 times 10 raised to the, I believe, 7th power, and this is in newtons. So this would be the thrust of a rocket if you were looking at this from a what is this force standpoint. For number 6, we have another boxcar, and it strikes a second car at rest. So here's my box, and it's moving to the right. So let's go ahead and say that it has, we'll call this mass of boxcar A is equal to 7,700 kilograms, and it's moving at, so this is, I should label this, sorry, V1A is equal to 14 meters per second, and it strikes a car that is at rest. So we're assuming that this is a car that we don't know the mass of, because it's asking us for that. So we don't know this mass. So we're going to say mass B is unknown. But we do know that V1B is equal to 0. Then, after these things collide, they move together with a speed of 5 meters per second. So together, they move off with a final speed of 5. The question is, what is this mass? So we just tackle this from a standpoint of conservation of momentum. So P1 is equal to P2. And let's set this up. Mass A times its initial velocity plus mass B times its initial velocity, which is 0, we'll get rid of it later, is equal to mass A plus mass B moving together at their common final velocity, V2. So I'm solving for mass B here, and I'm actually going to go ahead and solve this one without solving it symbolically first. And we're going to see that more and more often as we do collision problems. So I can go ahead and get rid of this because there is no initial velocity for car B. And actually, we can solve this symbolically first, so let's go ahead and do that. Why not? So MA times V1A is equal to, I'm going to distribute, MA times V2 plus MB times V2. Subtract MA V2, and then divide by V2. And I will have that mass B is equal to mass A times V1A minus mass A times V2 all over V2. So now I can substitute. Mass A is 7,700 kilograms times its initial velocity of 14 minus 7,700 times the final velocity of 5, all divided by the final velocity of 5. So plugging this into a calculator, we find that our mass B must be approximately 13,000, and I'll go ahead and write it all down here, 860, and that should be in kilograms. So, you can solve this symbolically. You did not have to first. And there you go, just another conservation momentum problem. For question number 7, we have a child who is sitting in a boat and they throw a package out horizontally with a speed of 10 meters per second. So here we have a picture already. We want to calculate the velocity of the boat immediately afterward, assuming it's initially at rest. So what's not stated here is that this is technically V2 for the package. because our child and our boat are initially at rest, because the child's in the boat. So mass of the child is given to be 24 kilograms. Mass of the boat is given to be 35 kilograms. They both have an initial velocity of 0, so V1 we'll say is 0. After the collision, we do not know what the velocity of the boat is, but it must contain the child as well, because the child did not throw themselves out. So now we have mass of the package, which was given to be 5.3 kilograms, and a final velocity of, we'll say, the boat and child. So I'm just going to do BC here, because that's the boat and the child. And that's our unknown. So this is a little confusing simply because you have two masses that are given separately, but really move together. So let's go ahead and set this up from a standpoint of conservation of momentum. So beginning with my easy statement of P1 is equal to P2. Mass of the child and mass of the boat, they're moving together. So they have initial velocity of V1. Mass of the package also has an initial velocity of V1. Then finally, we have the mass of the child and the boat that move together with a velocity V2, and the package that moves separately with a velocity of V2 for the package. So, thankfully, V1 is 0, so everything on the left side cancels out, and all we're left with is what's remaining on the right. So, I want to know V2 of the boat. So I guess I should label this V2 BC, I'm sorry. And so solving here, we start off with 0 is equal to MC plus MB times V2 BC plus mass of the package times V2 of the package. Move this over, so we have negative mass of the package times its velocity is equal to the sum of the two masses in the boat times V2 BC. And finally, just divide by those two masses added up. And so we see that the final velocity of the boat would be negative mass of the package times its velocity over the mass of the child and the mass of the boat. Whew! So let's substitute. Negative 5.3, now be careful, times the 10 meters per second that I did not write down up here, I should do that. So V2 for the package is 10 meters per second, and it's positive, it's to the right, over the mass of the child, which was given to be 24, plus the mass of the boat, which is given to be 35. So plug this into our calculator, and we see that our final velocity for the boat and the child should be pretty darn close to negative 0.90 meters per second. So this makes sense. If we throw our package to the right, our boat and child should move to the left. All right, so we have an interesting situation here where we have a bullet and it strikes a block. And then it comes out the other side, but the block is now moving. So let's put the block on some frictionless ground, and we have a bullet. So the mass of our bullet is given to be 22 grams. And while that's great, we typically want kilograms. So I'll go ahead and rearrange this and say it's 0.022 kilograms. So the mass of our block is 2 kilograms. So I'll write, we have wood. So we'll call this mass wood is equal to 2 kilograms. And that's the same before and after. Initially, so V1 of the bullet, we have a speed of 240 meters per second. After this bullet goes through the block, however, it is only going 150 meters per second. So we actually have a case where we need to know the fact that V1 for the wood is 0, and our unknown is actually V2 for the wood. So let's set this up as a conservation of momentum problem. P1 is equal to P2. So mass of the wood times V1 of the wood plus mass of the bullet times its initial velocity is equal to mass of the wood times its final velocity, which is what we're looking for, so V2 wood, plus mass of the bullet times its final velocity. So the only thing that's 0 and we can get rid of is the initial momentum of the wood because it is not moving. So now let's go ahead and solve this for V2 for the wood. So rearranging this, we're going to see that we have V2 for the wood would be equal to mass of the bullet times its initial velocity minus mass of the bullet times its final velocity all over the mass of the wood. So substitute our values. Mass of the bullet is 0.022 kilograms. V1 for the bullet is 240 minus mass again times its final velocity of 150 over our mass for the wood, which is 2 kilograms. So plug this into our calculator, and we get a final velocity of the wood to be only 0.99 meters per second. And there you go. So this is, again, just a conservation of momentum problem, but set up in a little bit of a different situation. All right, question 12 is a little bit more complicated. So let's write down all the information we're given. So we're given that a 0.1545 kilogram baseball, so the mass of our baseball is 0.145 kilograms, is pitched horizontally at 27 meters per second. Okay, so 27 meters per second. So we're given that our ball is coming in and it hits a bat. I don't know. This is a bat. Maybe a little longer. So hits a bat and then it goes upward and reaches some maximum height of 31.5 meters per second. Meters. So let's see. V1 for the ball is 27. And it's in contact with the bat for 2.5 milliseconds. So our delta t here is 2.5 milliseconds, which is the same as 0.0025 seconds. Okay, very short time. We want to know the average force between the ball and the bat during this period of contact. So let's start by just using our impulse definition of Newton's second law. So force is equal to mass times delta V over delta T. All right, so we have to figure out, in this case, we know mass and delta T, so we need to figure out delta V. How do we do that? Well, we're given the information that initially it has a speed of 27 meters per second. What we don't know is how fast it's going after the collision. So we need to find V2B based off of projectile motion. So how do we do that? Well, we're given a maximum height, so we can actually say that delta y is equal to 31.5. We know that up here it's going to stop for an instant, right? So we'll say this is V3 is 0. So we'll say V3 is equal to 0. Delta y is positive 31.5. G is negative 10. So let's find that initial velocity for a projectile. So we're going to go ahead and use the third kinematic equation here, which you start off as v squared is equal to v naught squared plus 2a delta y in this case. And so which one comes first? Well, v2 comes before v3. So I'm actually going to say that v3, which is 0, is right here. So v3 squared is equal to v2b squared plus 2a delta y. So v3 is given to be 0, or not given to be 0, but it's understood to be 0 because that's a maximum height. And so what we now have is a system we can solve really easily for v2b. So v2b is going to be equal to the square root of negative 2a delta y. So I guess maybe instead of g, we should have said a. Let me erase that and fix it. And so v2b is therefore going to be the square root of negative 2 times negative 10 times 31.5. So plug this into our calculator, and we find that our velocity after hitting the bat will be pretty close to 25.1 meters per second. So now we can go up here and we can figure out delta V. So I'm going to expand this a little. My force is equal to mass times delta V can be rewritten as V2 minus V1. It's a change in velocity all over our change in time. So let me zoom out for a second so we can see more. So if I want to find this force, then I'm going to have my mass of 0.145 kilograms times my change in speed or my change in velocity, and that is 25.1 minus 27 all over our time of 0.00, pardon my pen, 25 seconds. So plugging this into our calculator, we get a force of approximately negative 110 newtons. So we can say that it's negative. We don't really need to, but that does make sense because we said that the ball was coming in at a speed of 27 meters per second, but to the right. So for our bat to hit it, it's going to apply a force in this direction. Well, not really in this direction, but in the positive direction in order to change its velocity as such. So there's the magnitude of our force. All right, question 15 is another impulse question where we're given that the mass, pardon me, let me change my pen. So the mass is 0.145 kilograms, and our ball comes in at some initial speed of 31 meters per second to the right, and it's hit backward at some speed to the left, V2, and we'll have to say that this is negative 46 meters per second. Then we know that the contact time between the two things is 5 times 10 to the negative third seconds, and we want to calculate the average force between these objects. So let's take this from our definition of force with change in velocity over time. So we actually have everything except for our change in velocity. So let's rewrite this as mass times V2 minus V1 over delta T. Now it's pretty apparent that all I need to do is substitute 0.145 kilograms times negative 46 minus 31 over our 5 times 10 to the negative third, which we can rewrite if we like, of 0.005. And we find when we plug this into our calculator, we get a force of 2,230, I'm going to round it to. And that should be negative. Now, we really don't need the fact that it's negative. We just know that the amount of force is going to be 2,230 newtons, and the direction is just a choice based off of how we analyze the problem. So that we don't leave anything out, I also wanted to talk about our one discussion question. In this case, it was a multiple choice question, where two children float motionlessly in a space station. There's a 20 kilogram girl pushing on a 40 kilogram boy, and he sails away at 1 meter per second. So what happens? Well, here's the girl, and here's the boy. If the boy moves away at a speed of 1 meter per second, by conservation of momentum, the girl must somehow move in the opposite direction. The question is, how fast is she moving? So let's see. We know that she will not remain motionless. Momentum to be conserved, she must move in the opposite direction. So she's also not going to move in the same direction. Well, we know she's going to move in the opposite direction, but is she going to move at 1 meter per second? Well, let's think. If we want to conserve momentum, then the momentum of the boy must be essentially the opposite of momentum of the girl. So if the boy is moving at 1 meter per second and he has a mass of 40 kilograms, then his total momentum is something to the effect of, so PB, 40 times 1, which is 40 kilograms times meters per second. Therefore, the momentum of the girl must be the same. So, the girl must not be able to have a speed of only 1 meter per second. She must be moving faster. Well, how much faster? Well, let's see. So if the momentum is 40, then we can just say 40, actually let's do it this way. P is equal to mv, or v is equal to p divided by m. So we'd have 40 kilograms times meters per second over the girl's mass of 20, which is a speed of 2. It's just to the left. So here we want to move in the opposite direction at a speed of 2 meters per second.